If you plant a seed in pure, ground-up rock, it dies. We assume dirt is just crushed stone, but sterile minerals alone cannot support life. For soil to grow anything, it requires a biological spark. Productive soil is overwhelmingly inorganic, roughly 95% crushed rock and minerals. Our entire terrestrial food chain relies on the remaining 5%, organic matter. That tiny fraction of decayed plant and animal life is the sole difference between a barren desert and a lush, productive forest. The Earth grows food through an active biological engine composed of three parts: a physical framework, the chemical fuel, and an organic operating system. The engine starts with the physical chassis. This structure is built from three distinct sizes of pulverized rock: sand, silt, and microscopic clay. The specific mathematical ratio of these three particles determines exactly how much water and air the soil can hold. This textbook page defines the proportions for ideal loamy soil: 50% sand, 30% silt, and 20% clay. Notice the bullet point: debris larger than 2 millimeters, like gravel, isn't even classified as soil texture. But even with the perfect loamy structure holding exactly the right amount of water and air, this physical matrix is essentially an empty house. On its own, it cannot feed the plant. To feed life, the engine needs chemical nutrients. This infographic lists the essential elements required to grow plant tissue, specifically macronutrients like nitrogen, phosphorus, and potassium. Running out of these elements shouldn't be a problem on a global scale. Potassium, for instance, makes up 2.6% of the Earth's crust. Yet, despite this abundance, plants regularly starve for it. The bottleneck is that most of this potassium is not readily available, trapped inside hard crystalline rock. As these notes show, higher agricultural productivity drains loose fuel, leaving the rest inaccessible to plant roots. Without a specialized mechanism to crack open these minerals, the vast majority of the Earth's chemical fuel remains permanently separated from the biological food chain. Soil organic matter, or SOM, is the active system that bridges this gap. When this material decays into a stable substance called humus, it interacts with the physical minerals. Microbes living within the organic layer provide the first step. They constantly excrete specialized metabolic acids that target the minerals. Organic acids, like citric acid, physically react with hard silicate minerals, dissolving rock to free potassium. Microbes also use byproducts like alpha-ketogluteric acid to release phosphate for the plant. But once the fuel is freed, it is at risk. Without a way to secure them, these loose chemical nutrients would simply wash away into the groundwater during the next rain. Humus acts as a chelating agent. On a molecular level, it binds to metal ions, acting like a chemical claw. It grabs the dissolved micronutrients and holds them in the soil layer until roots can absorb them. That thin 5% sliver of organic matter is essentially a continuous mining operation, using biological acid to melt sterile rocks into digestible chemical food. Because this system is an active exchange, altering the environment pushes the three components out of balance. In a temperate climate zone, cold winters slow down organic decay, allowing a thick layer of humus to accumulate and store massive reserves of chemical nutrients. In tropical climates, warm, humid environments cause organic matter to decay so rapidly that humus cannot accumulate. Without that organic holding capacity, heavy tropical rains wash chemical nutrients out of the physical soil profile, leaving it barren despite the lush growth above. Ultimately, soil productivity is determined by the continuous exchange, where organic acids dissolve solid rock and decaying matter secures the released minerals. This calibration of physical rock, chemical elements, and organic decay is what sets the limits for terrestrial life.